Our next talk is from Thomas Maschmeyer from University of Sydney, and his talk has the intriguing title of Catalysis, Excitement and Utility.
Well, thank you very much. Well, given I'm privileged to give one of the JMT memorial lectures, I thought I'd choose a title that would have been JMT-esque in nature. So I hope I can get this going. So there we are, almost there. And now, all going well. Are we there? Are we there yet?
Yeah.
Okay. Now this thing's trying to set. Okay. Wonderful. So thank you very much again for giving me the opportunity to speak here today. Does this? Yep. So you saw an absolutely tour de force of tremendous science in greatest detail. What I thought I will do today is to give a bit of a high-level collage of my works inspired by John Thomas. And I will start off with a little bit of history, and we'll talk a bit about titanium, and some of the people in the audience will know where this is leading to. Then I go into some fundamental catalysis, trying to give the detail that John was always so keen about, and finally end up with technology translation examples. And the reason for that is one of his maxims was, this may be an interesting question, but is it important? And with the technology translation, I'm trying to show that maybe the questions were important, because the total value of the companies that we set up now is getting close to £1 billion, and we're trying to address some of the big problems that we have in waste and in energy. So tetrahedron titanium, some of you will maybe even remember this one. This is from 1994. At that stage, when I came here as a postdoc to the Royal Institution, titanium was the kid in town. We needed to know whether it was tetrahedral or octahedral, whether it was changing during reactions, etc. And the reaction was oxidation. And so my contribution was to put titanosil dichloride onto surfaces and making sure that all the titanium species were isolated, and we were able to look at them in situ. And together with Sanka, who's in the audience, we published a paper, and Fernando Rey, that I'm proud to say was my first paper with John Thomas, and is still his most cited paper. But it was very much enabled also by Sanka's fantastic work at the synchrotron, and we were able to show in one of the first operando in situ kind of studies what happened to the catalyst, not with videos as we saw today, but slightly more two-dimensional in time. And this picture here is a photograph of a silicon graphics screen with a very fancy bit of software and some black cloth in a room upstairs in the Royal Institution. So we have moved on. But so much for the history, good times and very exciting period. And of course, Sir John was always extremely inspirational in guiding us. So one of the things that he was always keen to emphasize to us was, with new techniques, I can ask new questions, potentially of older systems, but understand them better. And atom probe tomography is one of those techniques that has started to come really about, and we are able to look at non-crystalline materials in great atomic detail. And we've chosen something really simple, just a simple core shell particle, a gold core, silver shell. What could be easier? The color of this colloidal suspension, for those people who've been to the Royal Institution, is of course the same color as that made by Michael Faraday, the first gold suspension ever. And Michael Faraday, of course, was one of the big heroes of Sir John, and has written a book about him and given a fair few lectures, so I thought it was a good example to choose as well, just because of the color. What this ATP technique does, it's allowing us to take nanoparticles, put them on a silicon wafer, coat them with metals to stabilize the whole system, and then we take focused ion beams to cut out a needle shape, and at the tip of that needle is one of the particles, which we then irradiate with lasers to evaporate off an atom from time to time. And that atom then can be detected in terms of its atomic number and its position, where it came from. This is the experimental, which shows you what it looks like. So, we have a pointer here. Oh, well, it doesn't matter. So you can see the steps in the silicon crystal, which have got nanoparticles on them, and then we cut out, bottom right, left-hand picture, we cut out a needle with fib and lift that with a micromanipulator and put it into the ATP machine. What we found was something unusual. We expected the gold to be fully covered by silver, straightforward, but that's not what we saw. We saw this alloying kind of behavior. And to cut a long story short, the take-home messages there were that on the surface of this particle, we had quite a few spectator ions. We had sodium, which came from the synthesis, and also some nitrogen from the nitrates. And we were able to correlate the amount of alloying and the surface curvature that are due to the sodium especially. So this can often, I think, explain why the same synthesis, even from batch to batch, can vary, between people can vary, because these spectator ions are actually doing things. And we were able to look at this and understand it because of this new technique. Until now, this really was ignored, because you would just say, oh, I'm making gold and silver, how difficult can it be? And in fact, there's great amount of intricacy in that. And of course, then there will also be changes in catalytic activity, etc. So the other thing I learned, so that's for new techniques. The other thing I learned at the Royal Institution was the great power of combining computational work and experimental work, how those two things can really inform each other. And so this gives now a little bit more detail. What we try to do is we try to design a catalyst computationally, always challenging, but always successful, because you calculate it and you're sure it'll work. And the idea was we took formic acid and find a catalyst that selectively dehydrogenates it, so we can make hydrogen selectively and does not dehydrate it, which is the non-selective reaction. And we were doing that to see whether we could use formic acid as a simple storage medium for hydrogen. So here we go. This was done by Ruth Amos. She's now at the University of Tasmania. And we used the National Supercomputer Network, etc., to do the calculations. And we based our model on just an MFI structure, zeolitic structure, crystalline sponge, and synthesized then the kind of modifications that we looked at computationally and characterize them structurally, and then test for hydrogen production. So pretty straightforward conceptually. But the devil, of course, is always in the detail. So what we did first, just calculate some transition state barriers, looking at the formic acid adsorbing onto the active site, getting a lowering of energy. And then we see, of course, for the transition state, that higher energy. And unfortunately, the one we want, the dehydrogenation, sits above that of the dehydration. So we need to find a catalyst that pushes that down. So that's the framework of our thinking. And give you some numbers. Uncatalyzed, there is basically a very similar activation energy, transition state energy, very high for both dehydration and dehydrogenation. Catalyzed, as I just showed you, with a protonated ZSM5 catalyst, we have the energy selectivity, but it's but it's positive, so it's wrong. It makes us more, makes the dehydration more likely rather than the dehydrogenation. If I put sodium there, so if I ion exchange, I sodiate the zeolite, I get the right switch. So now my dehydrogenation is expected to be lower in energy, so I should get hydrogen predominantly. If I put some germanium into the framework of the proton form, I reduce the overall transition state barrier, but I do not have the right energy selectivity. If I sodiate that, I'm doing quite well. Okay, let's see whether this computational insight, translates into experiment. So we made all these materials, and the people in the audience who are specialists can see that, it sort of looks okay. One of the issues with framework substitution, so when we put germanium into the framework, is that sometimes there will be germanium on the outside of the framework. And so we remove that. Important point, and I'll come back to that later. So we remove that germanium oxide. Okay, so what happens then in terms of the actual catalysis? What we see is just, this is our reactor with some quartz wool, so nothing happens in the background, which is what we expect. Whoops. And now, what we see, irrespective of the material that we make, it all doesn't work. Everything makes water, doesn't really make hydrogen. So, given John Thomas's love for alliterations, is this a catastrophic computational calamity? Let's have a look at this in a bit more detail. Are there any acid sites remaining after the ion exchange? So, if I have defects in my MFI structure, if I have a look at silicate 1, which doesn't have any aluminium in it, if I have defects, then I have Silanol nests, and they can still be active, but are not so sensitive towards the ion exchange. So if I put in a silicate 1 with defects, I make a lot of water, so that might be my problem. So indeed, if I have a look at the transition state, the barrier for silicate for dehydration versus all the other materials for dehydrogenation, you see that those defects in my framework win. So I made all the right materials, the computational predictions were right, but the defects killed me. So does that mean that the project was over? Well, we had a computational student do this. And so she said, well, what I'll do is I'll just replace all the silicon with germanium. Now, anybody who makes zeolites knows that that's not possible. But, if you don't know, you try. So she did that, and she found that she made sodium germinate, which is what we would have expected. Well, she made it, and then she said, I might as well simulate it. And the simulation came out to be quite good. So the energy selectivities were in the right direction. And let's see what happens. So we all had the negative selectivity. So we now get a material that is 94% selective towards dehydrogenation. So without that interaction between computational and experimental, we would have never done the experiment. So we found this this very interesting catalyst. Now, of course, I want to have high surface area of my germinate. So distributing it on a material like a zeolite would be a good thing to do. Well, if you remember, we had some extra framework germanium oxide in the zeolite that I washed out. How about I don't wash it out? And indeed, I get very good selectivity towards towards the synthesis of hydrogen, towards dehydrogenation. And per germanium normalized, it's very good. So if I had not done that very careful experimental work, we would have wrongly associated the success of our experiment with a germanium substituted zeolite. So the careful work, the background experiments, really, really important. We also calculated potassium before, and we do this again, and potassium looks even better. We try it out synthetically, and what we see is, yes, it's not bad inside the zeolite, but I still make some CO. That's because of the silanol nest. If I just use a potassium germanate, I get 100% selectivity. So we ended up getting what we wanted to get through very careful steps in experimental and computational. So I think that really shows the great advantage of the two things working together. So that's for the detailed, more detailed catalysis single sites discussion. Now I'd just like to switch gears and talk a little bit about applied things. Yeah, is it really worthwhile? Does it make a difference? So waste biomass upgrading is one of those things. What you see there is Prince George in the picture. That's the world's largest biomass refinery, pulp and paper mill, 6 million tons of trees sustainably harvested. Their harvesting cycles are 120 years, so they look after the forest very well. So what I've done is with my group to work out a new technology called Catalytic Hydrothermal Reactor technology. It is based on subcritical or near subcritical, supercritical water or subcritical water. And that is basically steam that is so highly compressed to act more or less like a liquid and is able to dissolve things. And we are able to depolymerize organic polymers, biomass, brown coal, waste plastics, use lubrication oils, and make a whole range of different products, which I can integrate into the existing refinery streams, into existing infrastructure. And what does it do? So just give you an idea for the woody biomass, I have some sawdust here. It goes through our process, and we end up with biocrude oil. And that is, interestingly, the same amount of energy in each vessel. So it's very much more dense. And we are able to, of course, now it's a fungible material with existing streams in the refinery. So we are currently building the world's largest biomass plant in Prince George, 200,000 tons per year. And we are just being certified for jet fuel A. So airlines are now queuing up trying to get some of the material. And I think, you know, the key here is we're not growing anything new, is we're using what is there already in terms of waste and making better use of it. But when I have this brown group, this brown oil, what are the best processing paths for the upgrading? So there are three, in principle, options. The first one is just use as is. And in the maritime industry, that's a good choice. High sulfur fuels, bunker fuels, are very bad for the environment. We can dilute them down and help that problem to be mitigated. The other one is to use it as a blend stock in a refinery. So I just put in 10 or 20% into existing refinery streams. And given the volume of crude oil, that's all you can ever do. Or I can go for standalone new biorefineries, which need, of course, quite substantial investment. And there's a higher hurdle for the introduction. So, I just go through one of the three options, and that's the refinery blend stock. So what's the refinery path I might choose? We can go to make gasoline kind of materials, FCC, mild hydrotreatment and fluidized cracking, or a full hydrotreatment. And I just focus on the full hydrotreating, and we've done this work with Evelina Korma. And all of these operations are at huge scale, currently employed in refineries. So this is just for the specialists. We're doing a good job with micro-riser reactors using industrial catalysts. And what we're looking for is how does biocrude compare with light cycle oil in straight run gas oil blends. Whoop, bit of a mouthful, not as elegant as Sir John would put it. But straight run gas oil is the stuff that comes off when you distill the crude oil first. it's a very valuable fraction, and you want to dilute that as much as you can with less valuable material in a refinery to improve your profitability. So normally what happens is 20% light cycle oil is added. That's a lower value stream. And then it is hydroprocessed. So we want to see whether it's possible to put biocrude oil in. So these are the numbers after 50 hours on stream. I don't expect you to look at the table in depth, but just look at the fingerprint. So straight run gas oil in a GC analysis, what it allows us to do is we can look at saturates, we can look at monoaromatics, etc., and compare the different types of groups in these materials. So you can see biocrude is very different. So will this work? Doubtful. However, if I now compare the hydrotreated material with initially at the bottom right-hand corner with a light cycle oil, so the traditional way, that looks pretty similar, in fact, to when I put in the 20% biocrude oil. And for the specialists in the area, if you look at it, you'll see it's actually slightly better. So the summary is that we are making not just a like-for-like substitution, but it's better for like. We make a higher saturate material, we have lower product density, and we have composition close to the pure as straight run gas oil derived product, which is, of course, what you absolutely want. So we have a better material with our biocrude oil using existing refinery options. So that is a real big tick, I think, for this approach. Stability is always an issue, and of course, with the high oxygenates in the biocrude, there is the worry about making coke on the catalyst. And what we see here, after 50 hours on stream or so, we actually make a little bit less coke than the light cycle oil does. So we are in a very good shape when it comes to stability as well. This is what it looks like. So 0 is just a straight run gas oil, and then we add our biocrude, and it's getting darker and darker. But think of it like a glass of red wine. The color molecules are quite are not so concentrated, but still give rise to a deep color. This more smells like whiskey. So maybe there's another path if it all goes pear-shaped. Anyway, so if I put this into my hydrotreating, I can get my hydroprocessed products, and you see that they're beautiful and light and clear like water. Waste plastics. We have the same process, but we can tune it a bit, increase the temperatures, and really crack our bonds. And waste plastics are, of course, a huge problem. 20% or so of plastics, if I'm generous, are recycled now, but 80% are difficult to recycle. They tend to be recycled either as landfill or burning it, not best use. And a lot of that plastic ends up in the oceans. In fact, if current trends continue, our oceans will contain more plastic than fish by 2050, and some people say that's even earlier. So, we can appeal to people's altruism to behave better. That works up to a point, but in my life experience, appealing to their avarice tends to be more beneficial in terms of changing their behavior. So trying to make the plastic worth something is the way to go. And with our technology, it is worth something. And this may be of interest here because it's in the UK. The first plant of its type is being built in Wilton on the old ICI site right now. Concrete is being poured, steel is going up, cables are being laid. And that is a picture of that plant, by the way. And the green bit is the pre-sorting of the waste. In the UK, the rubbish isn't sorted quite as well as on the continent. And the little orangey bit is the actual plant. So what goes in is we have some water and an extruder and our waste material, and that's the same for biomass, and that goes into our reactor. And then once it's in the reactor, we add in a very special way supercritical steam. That took us about 5 or 6 years to perfect. That's where all the IP sits. And once we've done that, without exploding everything. And in the past, when we did it, we did explode it a few times. In fact, once we ran it, and there was a big explosion, like a really big one. And we thought, people might have been killed. We were all very afraid. And it turned out there was a substation a few blocks down, and a flash of lightning had gone into the substation and exploded the big transformer. But I aged about 10 years in those 2 seconds. Anyway, PTSD, I think. So it goes into the reactor, and then initially we make some gases, and the gases are used to actually run the factory. So we run the whole process. About 90% of its energy comes from the waste, and there's about 15% we're sacrificing of yield. And then we make plastic crude, and of course have to drop out the inorganic fillers of the plastics. And because supercritical water is unable to dissolve salt, it just drops out in the process quite neatly. So we can do all sorts of things. Yes, aluminium coated plastics, chip packets, no problem. Nobody else can do that. That's what comes out. 4 streams: naphtha, straight run gas oil, light cycle oil waxes, and the heavy residue. And they are all tradable, and we can incorporate them into refineries as they are. The inorganics go into brickworks or cement work. We have processed water. Most of that gets recycled. Some of it has to be bled off to keep salt concentration stable, but that can go into normal standard wastewater treatment. So the world's embraced this. KBR is our partner to roll it out. They've just put $100 million US in at a valuation of $600 million US. And partners are who have taken licenses on building plants actively. LG Chem in South Korea, Mitsubishi Chemical in Japan. Dow has committed to 6 plants around the world. The first one is being built, 125,000 tons in Germany right now. And Shell is a big partner for the biomass. So this is really being embraced by some of the big companies as the way forward to have our cake and eat it too in terms of plastic use. We've also, as a world first, made in Australia, 30,000 KitKats, which are wrapped by recycled KitKat wrappers, which was quite an achievement to get all the companies aligned in that circular manner. That's really hard. The science is comparatively easy. And so as a world first, we showed that it's able to be done, and Nestle is going to roll this out globally in their production lines. So do I have 3 or 4 more slides? Is that all right? Yeah. So the next thing is energy. So that has always been a strong talking point of John Thomas, of course, and he's written a notable review with Peter Edwards about energy. And so I was inspired in that manner to also have a look and try to build better batteries, because a lot of batteries have problems. And the reason I'm here is, of course, because of the symposium, but also I have an annual general meeting of a company, Gelion, that I listed last year on the London Stock Exchange. So that was a nice coincidence in terms of timing. What we've done is we looked at zinc bromide chemistry and used all of the advantages of that chemistry in terms of state of charge independence, 0, 100%, doesn't matter. Temperature, pretty insensitive, doesn't burn, these sorts of things. Very stable, very robust. But normally they have to be run as a flow battery with tanks, pumps, manifolds, control equipment. Not really what you think normally as a battery, right? A battery is just a thing that's passive, and you put somewhere and it does what it's doing. That's more of a chemical plant. So the scientific breakthrough was basically based around gels which are able to control how the ions flow inside the battery. And I remember when the Sydney Nano Institute was opened, Robert Schlögl came and was our opening speaker, and was drawing up on a blackboard some crazy idea I had about batteries. And he said to me at the time, well, if you can get that working, that'll be a real success. So I think it's going all right. So what we've been able to do is to take the gel and then change the way in which we make this battery into that of a lead acid battery. So we can interact with about 50% of the world's production capacity for batteries right now, which is still lead acid. It's still $45 billion US a year. So that market is under pressure, and the sunken cost of the factories, are just there. And as they become lighter and lighter in the rate of utilization, we can come in and convert them. 70% of all the steps of making these batteries are the same as the alpha lead acids, 30% are unique to us. So it's a reasonably straightforward retrofit. So the breakthrough was that I worked out all the issues that we get that need flow, hydrogen evolution, pH drift, also segregation, all has to do with the bromine bromide not staying where it's supposed to stay inside the battery. The gel was able to dynamically accommodate the change from bromine to bromide and back and keep it locked where it's supposed to be. And that enabled then for the whole design to be changed, and that then enabled all sorts of other concepts and implementations down the line. This is sort of, what things look like when you have an initial idea. On the left-hand side, they're all very messy. I mean, if you have a very close look, it's bits of wood and paper clips from the office. That's how you start. And then you go further and further into more production-type materials and designs. This is what we've ended up with. It's basically very much like a lead-acid battery. And this is just some data to show you the temperature range. So -20, not a problem. Plus 55 degrees, not a problem. That's really, really unusual for batteries. That doesn't normally happen. That's one of the advantages of the zinc bromide chemistry. But they're also really fire resistant. And this is an Aussie battery. And of course, Aussies and barbecues are synonymous. So we put a hand-built one onto a steel plate. And underneath that steel plate, we have an industrial burner, gas burner, about that size with a big flame. And we get this up to about 600-700 degrees. We charge the battery. So it's a fully charged battery. And you can see a little light at the top and a time signature. And let's see what happens when we barbecue our battery. So after 10 minutes or so, you see some smoke coming, but no fire, no explosion, no nothing. So this is sitting on 600-700 degrees, right? Just imagine a lithium-ion battery do that at full charge. And after a bit more than half an hour, still a bit of smoke. So Leaning Tower of Pisa situation here, but no fire, and the light's still working. In fact, once it was cooled down, we were able to charge it and recharge it. It lost a little bit of capacity because we lost a little bit of battery in the process. But other than that, we were good. So we are very proud that just a couple of months ago, we opened our first small factory, a retrofit of a lead acid factory in Sydney. And there our two federal ministers, Energy and Climate Change, Chris Bowen and Ed Husic. And you can see the batteries have now evolved into more industrial design that one of the ministers is holding there. So, of course, things are not done in isolation. I'm really, really grateful to my group and the Julian team at the bottom picture there. The top picture was just taken a few days ago. We went on our annual Christmas do, and the group selected axe throwing to bring out our inner Viking. I think it's really therapeutic, actually. If you ever done this, it's a very therapeutic kind of thing. But lots of course, grant agencies and companies and people who've been helping along the way. But the person and the thing that really has helped me most in my academic career and really sort of been a shining light for me and inspired me and still inspires me every day today is John Thomas. So I'm very, very grateful to have been able to have the opportunity to give this talk today. And thank you very much for your attention.
Thank you very much, Thomas, for a talk that has fully justified its title. Again, we've time for 2 or 3 questions. Graham?
Try and shout.
Daniel's on his way.
Thomas, fascinating, wonderful, excellent. And one small question though, because at one point you just sort of in passing mentioned supercritical water. Now this is a really nasty beast.
Yes.
really, really nasty piece. How do you contain it? Because
Right.
other companies, one not so far from where we are, tried to do catalyst recycling using supercritical water, and the plant disappeared.
So yeah, excellent question. So supercritical water, yes, in passing. It's about 450 degrees the way we use it, and 220 bars, and the water itself becomes really aggressive. But it also is able to donate its hydrogen. And so the problem that we find, and that's a good research question actually, to really see proton radicals under those conditions, to prove what must happen retrospectively, because we get these plastic, you take plastic mixtures and you go through normal pyrolysis, and what you get out is horrible. What we get out is it's sort of a bit like baby oil, slightly colored, depending what we do. And that can only work if you stabilize the radicals that you're forming. And the way that is most likely happening is from protons from the water. But really, really reactive water. The reactor itself is lined with it's a high performance steel. But when it's not supercritical, we can use lower grades of materials. And because of the way we introduce it, we can make that reactor quite short, and a lot of IP sits there, so I can't tell you. But we have used the same reactor in our demonstration plant for 8 years, and it still looks beautiful on the inside, because from time to time we look down with the endoscope and we look at our wells and have them certified because of the pressure. Yeah, and there's a lot of IP in that. If you just go and buy from your local homeware shop some metal pipes, they'll just blow up. So it's a very carefully designed piece of equipment.
She'll chat to you in the bar.
Yeah, I keep
Yep.
My question is also actually about that plastic recycling, about whether this balance between effectively energy recovery and useful chemical recovery from the process, whether you, well, first of all, whether you try to recover anything more useful in the more volatile fraction,
Yes.
ethylene and things like that, and also whether you try to optimize that, because there's this argument about whether this really constitutes recycling. Much of what's being done is actually energy recovery. So I mean, I appreciate it's better than incineration, anything better than incineration, but are you trying to work on improving that balance?
Yeah. So very good question. So in terms of carbon balance, we get out of the mixed plastics, we recover about 98.5% as either gas or liquids, only a very tiny bit as a solid. In terms of the energy we use for the process, it represents 15% of the carbon going in. And we're just burning that at the moment, because separating the gases is too expensive for what you do. If we go and increase the amount of gas, the energy balance becomes much worse, and you're starting to get those questions that you just made. But I think, if you have your 15% of the waste going in and that runs the process, it looks pretty good. And also from an internal rate of return, it looks fantastic.
Good. Just a quick query. I mean, the fascinating work you're describing on biomass and plastic, you can kind of implement your technology in existing refinery plants.
Yeah, so certainly what comes out, our products, they can go. So everything is designed to try to get the lowest hurdle of introduction. So we have, so all of Shell refineries are formally allowed to buy our products, and Chevron as well.
I think that's a really significant aspect, that you can use existing
That's
plants.
right. And we've just been certified from the biomass for jet fuel A as well.
Okay, well, look, thanks very much again.
Thank you.